Hello everybody, thank you for coming. I'm very happy to be here with you. I'm going to share with you my research in the field of hardware reverse engineering. That's a thing I do since now over 10 years. And I created my company like 2.5 years ago because to me hardware reverse engineering and hardware security is something that should be taken very carefully because all of the code, the embedded things will be on some device at some point, some chips. So it means that the chips itself must be very secure to keep your secrets. Over the years, I've been told that hardware reverse engineering and hardware attacks were something that it's a threat, but it shouldn't be so big because the time and resource involved are pretty big. You need some big equipment, the study can be very long, and so on. So everybody says, okay, we know about the threat, it's a threat, we know that the attacks can give very nice results, it's effective, but you know, it's the number of attackers is too low, and mostly we don't care. And this reflects also in the evaluation criteria for the cards, because for the same reason, time and resources, the criteria doesn't take care enough for me about this kind of techniques. So that's why I created my company, because I wanted to investigate two things. So first of all, what can be done with hardware reverse engineering in terms of piracy, in terms of hardware backdoors, in terms of IP theft, in terms of obsolescence too. And at the same time, I wanted to experiment on it. And I was sure at the time that we could make the time and resources reason disappear, because that's the point. I think we can analyze hardware pretty fast, and that's the subject of this talk. So for this talk, we will demonstrate how a group of pirates will attack this card. So this card is a pay TV card, so we will talk a bit longer about that. But the goal for the pirates will be just to, this is a black box for them, you know, they take the card, they just remove it from plastic and just have a look on it, you know, and say, okay, so we have a card, what's the architecture, we don't know about it, and what's inside the memories, so they don't know about it, they want to dump it. So we will see today how we can extract these kind of things in a matter of weeks, not months like before, in a black box situation. So I will start with some background before jumping inside the card, you know, just to give you an idea of how hardware security has been taken into account over the years. So the background is we will focus on secure microchips. So secure microcontrollers are all around us in our pockets, because it's ID cards, it's banking cards, it's cards, you know, cards everywhere, but it's also present in video game controllers, printer ink cartridges, and all of the consumable that must be protected to make sure that you are buying the right brand. So in this situation, we have this secure controller everywhere, and we have invasive attacks. So I won't speak about side channels, I won't speak about non-invasive attacks, because for me, if I have to dump a chip, let's say for example there's a pirate card somewhere of some sort, and I want to extract it to find a way to build countermeasure, I will do an invasive attack, because I know my chance of success is very close to 100%. And with the techniques I will describe, it's 100% and it's pretty fast. So that's the whole thing about the talk. So when we are speaking about hardware security, I have to speak about pay TV at some point, because they were mainly the first market to suffer heavily from this kind of things, you know, because as you know, the signal is broadcasted to everybody, so everybody gets the signal, and the only thing you need is to have a key, so it's called a control word, which is decrypted by the smart card over there. So if you have the control word, basically you can decrypt the channels and watch TV for free. So it didn't take too long to see those kind of device to emulate official cards. So that card is mostly the same as the original, except that it decrypts every channel, and that the expiration date of the subscription is like in 2 years or in 3 years or whatsoever. I think the battery will die before maybe. Anyway, so as PayTV got this problem a lot, you know, they were the one that were pushing the hardware security scene, you know, and as you can see, in 20 years, in 10 years almost, in 10 years, the amounts of countermeasure and sensors and shield and things like this was growing constantly and rapidly. And so now when we are speaking about smart cards, it's a complicated device. It's not just like before where you can open the chip, look at it, understand mainly how it was working and just try to extract it. The thing is completely different. Now it's pretty hard. But at the same time, so PayTV was pushing the security, the hardware security market, but we are seeing like a straight globalization right now. So it means it's not only PayTV who has the problem of piracy, because piracy is just one thing, but there is supply chain security, which is of major concern because most of the people design chips, but they don't build them themselves. They send that to a chip fab somewhere, and they got the chip back, you know. And they can't know if the chip they got back is the one they designed, or if there's a backdoor or something. So that's a critical issue. But also, if somebody is able to reverse the card, it could steal some IPs or stuff, you know. So the security on the card must be very big. And the biggest thing that I see coming, and it's already there in a way, it's counterfeiting, because PayTV is a small market, you know. But if you can now clone any ink cartridges or any consumable whatsoever, you know, you are reaching a mass market, and for pirates, it's the way to go. So at the same time, we have the Internet of Things with coming and fast. And it's the same thing. We will rely on secure microcontrollers that will be all around us. And it will push the security demand when the pirates are already doing counterfeits. So you see that it could be a real critical issue. So anyway, so that's just for introduction, but let's jump now to this little card. I will first explain the approach we were taking for this talk, because it's a research project. So it's a research project that we wanted to be as close as possible as a pirate scenario. So this card for me was a black box. And I choose to spend not too much time. I choose to try to look at a PayTV card, because it's supposed to be a very nice card, and it is. I mean, this card was on the field for, I don't know, more than 7 years, never hacked, and nobody was close to get to it, you know. So that's pretty cool. But if you're asking me now which specific vendor this is, I won't give you the answer, but I can just say that what I will present today is applicable to any smart card, any secure chips. Almost from smart cards to SoCs, you know, complex SoCs. So if you have an SoC, of course, it's a bit more work, but it will be still the same approach, and you can do the same thing. So what I want to focus on will be the analysis method, because when I was starting this 10 years ago and we had to extract a chip, it was pretty funny, because we had to take pictures with a microscope, you know, put the pictures together, and then we were tracing lines by hand, you know, with Photoshop. And it was pretty painful, and it was pretty time consuming. And at some point, Photoshop was crashing, or it took 10 minutes to save a picture, or your computer was too old to not enough RAM, or whatsoever. It was pretty hard. So we choose the whole process, and that's what we are talking about. We will also talk about the chip preparation, because to me, that's not the biggest part, but it's a big part. If you can prepare the chip well enough, it will simplify your life for the rest of the analysis. So the first step for this is failure analysis techniques. So it's sample preparation. So we have like the integrated circuit, we want to deprocess it. So the integrated circuit is like a stack which is like 10 microns thick with interconnect layers and transistor at the bottom, you know. And we want to image that. It's a secure IC, so I expect to be a technology that is already quite small, not the smallest one, but like 90 nanometer or maybe a bit below. And when we are talking about this feature size, it means that we can't rely on optical pictures anymore, because you will see it's not feasible to trace line on optical pictures because you see nothing. And then the assisted analysis, which will be the main part of the talk. So I opened the card and I was looking at the material. And when I was removing the plastic, I removed also the passivation, which is an oxide layer on top of the chip to protect it. And the chip was looking like white, so it's already an information. The chip is made of aluminum, and it's a technology that I like a lot, because it gives you a choice for the process, which is pretty straightforward. If the chip is aluminum, the via are made of tungsten. And this difference in material gives you the ability to etch the aluminum, and the tungsten will not be etched away. So it means you can reach this kind of pictures where you have like three colors. The black is the traces of the lines. Lines are not here anymore. We just see the profile of them, you know. The white is the via going down to the layer below. And the rest, so the gray thing, will be the oxide around the lines. So it means that if you have these kind of things, maybe you can, you know, threshold the thing and separate the features and automatically detect them. And that's what we will do. So once you did this deprocessing, you will make some imagery. So on the left picture, you have an optical picture of the chip. And as you can see, it's very hard to follow a line, because we see like big blobs of many lines. And if I want to trace one, you know, it's almost impossible. And it is with modern chips. On the right side, you see a SEM picture, so scanning electron microscope picture. And what we see is a standard cell. And you see that the polysilicon gates may be like 90 nanometer wide, and it's taking like 100 pixels, you know. So you have enough resolution to deal with the chips, even with the smallest features on the chip. So the chip we are looking at have like 5 layers. It has a shield too, but I won't show you the shield for a simple reason. It changed nothing in the analysis process, and from my experience, I don't know a very nice shield. I don't know a shield that I can't bypass, or that I can't just go between the lines or something. So I won't speak about shield. I will just speak about the core and all the things. So we have like the 5 metal layers. So the poly picture, on the poly picture you will see the active areas in gray, polysilicon lines, so it's the thin lines on it, you know, and the white via that are going up to the metal 1 layer. Metal 1 layer, so as I said, I removed the lines, so we see traces of the lines, and the via going down. Metal 2, same thing. Metal 3, same thing. Metal 4, same thing. So we had like 1,500 pictures per layer, which is like average size for a smart card. It's not too big. It's already big. I mean, you need a big hard drive, but it's not the biggest thing on earth, you know. So the fact that we moved to SEM pictures is something that gives us a lot of trouble. For one simple reason is they are distorted. And if you ask your SEM vendor to have like tables for the distortion or something, he will say, oh, okay, I didn't know it was distorted, you know, so you have to find a way to correct that yourself. So that was one issue. And it's a big issue because now you have like a lot of picture, and as I said, 1,500 pictures to me is not a lot of picture, it's some pictures, you know. But if you have like already 1,000 picture, when you want to correlate and stitch the pictures together, it could be an issue, you know. So it's an issue for aligning the pictures together, but now you have to align layers also together, and you know, it must be accurate enough that you can trace the signal inside the core of the chip, deep inside the core of the chip on many layers, and this can be tricky. And on top of that, you have the standard cell. So I wrote gates here. I should have written standard cells. When I was learning electronic, I was taught that this was gates, but chip vendors say standard cells. So I'm sorry for this. But anyway, so we have all this problem, and for us the solution was to write like a tool. So that's what I did. I was writing a tool. So it's called ARES, Automated Reverse Engineering Software, and it's made to address all of these things, you know. So it's made for extracting the features, but also create the images together, make the stack, and now you can trace the things inside, display a graph, and so on. So that's what we will do. So first step of the study now will be to extract the feature. So we have the same picture, and we do some math on it, and we get the extracted version of it with lines, via, and we can do this on all the pictures. We can do the same thing for the standard cells. So it means we have like metal one and the poly picture of the same standard cell. If we put that together, we have this extracted version of it. We can study this pretty easily. This is like an OR gate because you have the PMOS transistors are above. It's the big active area. The NMOS are usually smaller, and you can just by eye see what's going on. So okay, so you do this for all the chips. So now we assume that we have extracted every feature of the full core of the smart card, and now we will see what we can do with it. So if we go back to this card, so what do we see? So first of all, we can already see a lot of things. On the bottom left, this is all analog blocks that I will not speak about because it's not interesting for me to dump the card. It could be, but in this case, I will do something else. On the bottom right, on the top right, sorry, there is 2 blocks of RAM. On the top left, there is a ROM, which is pretty big. And the other memory, the blue thing, is the flash memory. And all the rest, this green thing, which is a bit like a duck for the shape, I don't know, is the core. It's the digital circuitry that drives the chip, you know. So as I said, we extracted every feature. So all this orangish thing is the core, the features of the core extracted. But we did the same also for the standard cells. So every of the green points is a cell inside the core. So for that particular study, there is like 22,000 cells that are displayed here. It's not all of them, but it's enough for doing the study. So you have an AND gate here, which has been extracted and converted to GDS2 file, but we will come back again on this point. All right, so what the attacker wants now is to extract the memory contents. So when I see all of this memory, of course, I don't want to extract the RAM. I want to extract the ROM, and I want to extract the flash, and I want to know which is the main memory and so on. So let's speak about the flash first. So it's easy to spot a flash with optical pictures. Oh, by the way, this is backside pictures. All of the optical pictures we will see are backside. So backside, it means I remove the bulk, so no more silicon bulk, and I can just look through the card like this. I think for me it's the best picture to quickly get information about where are buffers, where are memories, where are the blocks. You know, it's pretty useful. So when I see this, I see on the bottom there is like these white rectangles, and those are capacitors, you know. And if you have a flash or an EEPROM, for sure you have a charge pump attached to it because the flash or EEPROM to erase or write itself, it needs to have like high current. So it needs to build this up, you know, and it can't just take the 5 volt that comes to it and generate this, you know. So it's using this structure, which is the charge pump for these 2 operations, writing and erasing. So it means also that knowing that this is the charge pump, I can just switch the high power line, and now the chip can't erase or program itself. This can be very useful because in most cases, for example, if you cut the shield and there is a security interrupt triggered, but the charge pump now can't erase the flash, there's nothing that can prevent you for just doing a reset and starting again, you know. So it's pretty useful to know where the charge pump is because it's something that you can easily cut to avoid like chip erasure when the security interrupt are triggered. All right, so this is the flash. So I want to read it now. So I need to find the output buffers. Output buffers are over the top of it. So you see like these little rectangles repeating, and you can see on the zoom-in version the thing. And so I said backside picture are interesting because, as you can see, we can still see at least, I would say, 2 or 3 metal layers beneath. So the interconnects, we already see it, and that's also a good thing, because I can quickly spot where the output of this thing is, and I can already trace it, So what we saw is that it's just, you have like a number of outputs that are just divided in 2 groups, and it goes on both sides of the flash. So now we need to find the right place to make the extraction. And I suppose that this is a secure chip, so it must be encrypted, at least encrypted. So we can't just extract the data here and think we will be done. That won't be the case. We will have like encrypted data, and we will be able to do nothing with it. So just for the experience, I tried to trace the output of the flash to the core with optical pictures. It was painful, and I could only trace one line for sure. That line was going inside the core, so that's the line arriving inside the core, but that's the only one that I could trace to the core, and it's a bit frustrating. And that was the stressful part of the study, because, okay, I will give a talk at Black Hat, and now I don't know where the flash arrives into the logic. That's pretty bad. But anyway, so we found only one, but to me it's enough, because now we can trace it and try to find the others. So the method we were using for the old study is like a method where we think that the deprocessing quality is average. It's not perfect. We also think that the image quality is not perfect. And therefore, we assume that the feature extraction is not 100% accurate. So we have two choices. We can say, okay, it's not perfect, but what we will do is we will correct everything before starting the study. We will check every feature. Is it correct? And we didn't choose that route because what we wanted to do is not extract the full flat net list of the chip. It's just trying to find a way to extract the memory in the shortest amount of time, and without using heavy equipment such as focused ion beams and stuff like that. All right, so we did what I called line tracing. So it's like in Photoshop, but if you automate the task, it's a click on a line, and now you know where it's going. It's already connected to the standard cells and so on. It's building graph, the Verilog file, and everything at the same time. So for you to look at the study, it's very comfortable. You don't spend like a day to follow a single line. In a day, you follow like everything. So what I did first is I have only one output, and I wanted to know where it was going. And this output is going to 2 multiplexers. And multiplexer structures are very like inside the chip for a good reason, because if you have a multiplexer, it must have 3 inputs, so 2 different outputs and a control signal to decide which one will go to the output, So it means you can just follow the control signals to find all of them, So if I have 2 multiplexers, if I follow now the selection signal, I will find all of them on the same bus, And this thing is pretty nice, because if I can follow all of them on the same bus, I can trace them back. So this is a view inside the software with some of the gates traced and so on. And this is what happens when we trace the signals back. So now I know where all of the outputs of the flash are going inside the core. And I'm sure of it. It's not like, it could be this line or the one next to it. No, for sure it's this one. So it doesn't mean anything. I mean, you can't extract the chip at this stage, but at least you know what's going on. And so what we saw also is that the selection signal, so it's going to the muxes. We have the flash output going to it, and we were trying to make sense. So it's like you can change the order of the bits, inside the word. And it could be Indianness or it could be something else. But to me, it's not relevant so far to try to guess what this is. We want to dump the memory, so we have to follow now the output of the multiplexers. And that's what we did. So we followed that, and there was 2 paths, One path with combinatorial logic, could be like S-boxes or light encryption, very light for me, and there's a direct path, but they both go back to a multiplexer and you have one path at the end of it. So again, to follow this is pretty easy, and you have the example of what the software is giving us as a visualization. So the visualization part of the tool is not super fancy yet, but it's far enough to get the information you want. Anyway, so after a day of work, and I say a day of work, we get to this point where we followed the two paths coming to one, then there is another MUX, then there is also combinatorial logic, so it could be also scrambling something, S-boxes, and then we have like registers. And here I wrote instruction register, but that was the biggest part of the study, because at that stage, you don't know if it's the instruction register. You just know that there is a register there. If it's the instruction register, it would mean the data is in clear, and I can extract the flash at this point. I don't have to look at something else. This is enough, you know. So that was the main part of the study, was to look just after what was going on. Because if this is the instruction register, I should have the instruction decoder just after the thing, you know? And at that point, what you should see is, so the instruction decoder is usually the biggest part of the logic, or at least it's big, pretty big. And so we decided to check inside if we could see a grouping of bits, you know? Like, okay, we see that here it's taking 6 bits, sorry, or here it's taking 12, here it's taking 8, and it's grouping the bits like this, you know? Because when you have this information about size of groups, you just need to look at some data sheet, you know? Like you take PIC, Avier, Motorola, you take data sheets, you know, ARM, and you look at the instruction sets, you know? And now you try to find the same group inside the instruction sets, you know? And once if you can find that, that's the nicest clue to tell you that, okay, that's the instruction register. So that was the case. That is what we thought. So once we compared and have the match, okay, we have the instruction register. It's really bad at that stage, because I'm sure now that the data at this stage is in clear, the flash is the main memory, and I can just look at the register, and I can already say, okay, I will dump the chip at this point, you know. And it was really bad, because the lines that are going to the instruction registers and that exit the instruction register, they are all routed from metal 2, let's say, to metal 4, so to the top of the chip. So you don't even need to do some fancy fib editing to reach the lines. They are on top, you know, and that's really sad to see such thing. So anyway. Next part is just to study the instruction register, and each register has some control signals, and we found the control signals that for us are the best one to make an attack. One is like a clock or a read signal, which is perfect for synchronization. It's very useful to have this when you have a secure microcontroller, because one of the countermeasures that is usually used is jittering the clock. So your clock cycles are like moving this way, you know. So it means if you need several acquisitions, you can't sync them together. But there's also something else. It could have like a clock stealer, meaning that some of the clock cycles just disappear, you know, randomly. And now if you do several acquisition and you are missing some clock cycles, you're completely lost, and your bits don't match the inside the bytes and so on, and you can't extract the data. But if you have this signal now, you can just dump the chip, and you have like a tick, like a clock, to tell you when to sample the data and when the data is okay, you know. You have also another thing, like the enable signal. Enable signal is the signal I like the most on registers, because it prevents the output to be updated. So it means that I can completely lock the register in a state. The output will not move, whatever happens at the input. And so we have synchronization, an enable, and we know that the data is in clear So at that stage, we know that we can make a linear code extraction. So linear code extraction is very, it's an old technique. It's a very old technique. Before, people were just cutting lines and shortcut them to the ground. It was enough to dump chips. So now it's a bit more tricky, but if you can play on the enable signal, you can start to be linear at the position you want. So the whole point of linear code extraction is to extract the full memory content in the address order, you know. So it's address 0, let's say address 0, data, address 1, address 2, address 3, and so on. So you extract the full memory like this without any problem. So what happens usually now is that the chip will not start at the address 0, it will start at the end of the flash with a jump to somewhere in the beginning. So you don't want to be linear at the beginning, because otherwise you will get just the end of the flash. So you want the chip to be able to jump to the beginning, and now you want to trigger the linear code extraction. And that's where the enable signal is very important. I didn't mention that, but you can also, so I put 4 needle linear code extraction. You could do it with 3 needles, but if you do it with 4, it will give you extra redundancy to sync the bits. So it means for the extraction, you will have 1 needle on the clock signal, which will be for sync. 1 signal on the enable signal, where you will play with it actively to trigger the linear code extraction. And then 2 needles on the data bus. 1 will be fixed, and the other will move on the lines. So if your processor is like 8-bit wide, you will do 7 acquisition. If it's 16, it's 15, and so on. So flash is extracted at this point. It's just a matter now of going to a fib and do his thing. I just want to show you an old chip, just to compare, you know, because when we speak about old chips, the whole thing is different. You know, we have like the EEPROM at the bottom. On top, we see multiplexers. It's very easy to spot just looking at the lines and the way they are structured. And on the top of the picture, we have the core. We can also very easily see that it's the core because it's all messed up, you know. And in between, we have like the structures, 8 and 8. And with line going from the memory to the structure and from the structure to the core. So it's very easy now to know it's output and input buffer, and you already know that you can make the linear code extraction there, done, you know. It's a matter of like, I don't know, 2 days or something. But that's not what we have with modern chip, where we have to jump inside the core and check, you know. So when we have to go now to the fib to really extract the contents, it can be problematic, you know, for many reasons. So I spoke about shields. So even if I don't think that shields are good, it's still something that is preventing you to reach the lines very easily. Then, depending on the lines you want to connect to, you have to go from the front side or from the back side. And backside edit can be very difficult to do because it navigates inside the fib with the chip silicon substrates visible only. Could be tricky because you have no reference point and you have to create some and so on. But going from the front side with modern chip is the same, in fact, because people just planarize the chips. So it means they just take like a polishing machine, and at the end of the process, when they deposit the last oxide layer, they just make it flat, you know. So inside the FIB, a flat surface of oxide is just completely dark, you know. It's just black, you know. So the good thing with the method we were using is we extracted every feature of the core. So we turned that into a GDS2 file. So GDS2 files are the files that are created by the chip manufacturer for just manufacturing the chips. So we have like those files, and those files, you can just put that inside the machine, you know. And now you navigate with this overlay, so you precisely know where you are, where you want to go, what you want to reach. So it makes your life very, very easy. I remember in the past just digging holes to try to find like places I can connect to, and it was very difficult. When you have this kind of ability, it's like it's very comfortable. So anyway, so with all of this, flash extracted, check. So let's look at the ROM now. So the bits in a ROM could be anywhere, you know. It could be dopant, it could be via on between the active areas and metal 1, or between metal 1, metal 2, or whatsoever. It can be anywhere, you know. So the thing to do is just look at every layer and see if you see a difference. If you don't at the end of it, you know that the bits are coded as dopants. So I read somewhere that people could do backdoors on an integrated circuit with dopants, and that this is impossible to spot. And I never understood this, this claim, because if you have like dopant, if you can make a dopant etch, so you will see that you will have like white thing that will remain and black thing that is just dopant that have been etched away. So it makes a difference now between the kind of dopants, so you can read it. So it means that at this stage, we can just extract the raw bits. We don't know if it's encrypted or in clear, so we can check that, but at least we can extract them. So we used the tool, and we did the same thing that we did with the flash, meaning that we just traced the signal and we just looked what it was doing. So the ROM is encrypted, and this we knew since after 2 minutes of the study, because we found some XOR gates, everywhere, and it's a good sign. I mean, when you have XOR gates, you have an encryption almost for sure. So we could also check several things. We figured out that the ROM and the RAM. I will talk about this later. Sorry, but we found out that on the same path we had muxes and we had flip-flops, and this was confusing. But it can simply just tell that the decryption of the ROM is taking several clock cycles. So, okay, we know about that. So we know that it's encrypted, and we know that if we follow all of these gates, we will have the decryption mechanism, So we have the raw bits, we have the decryption mechanism, we put that together, and we have the ROM in clear. So we didn't finish this part because it was not interesting to have the clear ROM with us for a legal reason, especially. So, but to extract the ROM, I won't use any machine. Pictures are far enough because you have the raw bits and you have the decryption mechanism. The hardware is never lying. So if you can make a picture of it, you will find what you're looking for sure. It's 100% success. There's nothing to it. All right. So then finally we wanted to finish with the RAM. And there's 2 blocks of RAM, and same thing, it's very, very easy to spot that they are both encrypted, and that after there is a flip-flop, but we don't really care about that, and then there is a mux, and then there is again some kind of scrambling and encryption. And okay, so we know it's a secure chip, so everything is encrypted on it. It makes sense, But we also know that if now I want to use like laser fault injection to change a result or a register value or something inside the RAM, the chance of success is pretty low. I mean, I will change it, but with the entropy of the encryption mechanism, I will change a lot of bits where maybe I want to change only a few or just maybe one, to get access to another page or something. So that was enough for us to study and say, okay, this is encrypted. We won't play with like laser glitching or EMA or stuff like that. Anyway, so I will now go to a kind of conclusion. So it's a long conclusion. Get ready for it. I want first of all so we will be very fast on that one, but just to compare timing of all the different attacks that I see in my work life. So that is something that if I have this chip today, it's within a week it will be extracted. Because this chip has absolutely no security. It's not good. Then I want to show you this chip, because this chip was something we did by hand with Photoshop. So line tracing inside the core. So it will be a good comparison between the smart card we just studied, the PayTV one, and something which is not PayTV. It's not as secure, but we had to do manual tracing. So that's a 8-bit processor, and when we have when we study the flash, so these 2 blocks on top is only 1 flash, you know. And if you see, there is a gray area in the middle of the picture, which is the same picture we see there, and we see that there is 32 outputs. So 32 outputs for 8-bit processor, for sure there's like a multiplexer somewhere. But these 32 lines were going directly inside the core. So we knew that we had to go inside the core if we wanted to find the magic spots to perform like a linear code extraction, for example. All right. And so that's what we did, you know. So we wanted to find these 32 to 8-bit multiplexers with Photoshop and line tracing. So we found that there was 3 different paths to follow, and the 2 first were not usable for us. So there was one, like you have 32 bits, and you have some gates, and at the end of it you have 1 bit, you know. So it's hard to think that there could be an instruction register there, because I don't know any 1-bit processor. Second path was a bit better. I like it, but we couldn't use it at the time. So we were finding multiplexers, and then we found some flip-flops, and it in fact was latch. Okay, latch. And this could be it, you know, but then we followed the output of the latches, and it's just like a chain, you know. So it's, again, it can't be the instruction register, because you need to have like the 8 outputs going somewhere in the instruction decoder and doing something, which was not the case. We finally found the right spot, you know, with multiplexers and instruction registers, and as you can see, there was the 2 same signal on the latches. Clock, so a kind of read signal for synchronization, which is very useful, and then the enable signal, which give you the opportunity to just navigate inside the code. You know, you could you could, like, for example, get the running code and see some branches and say, okay, I want to test this branch, and with the enable signal, you can choose if you want to branch or not. You know, so it's pretty magic. But just to do this, so it's not that many gates. I think it's like, I don't know, like 300 or 400 gates, you know. And it's we didn't go deep inside the core, and there was no encryption. The data wasn't clear. So we could have just taken the 32 bits, you know, and then it would have been difficult to find the right bit order, but why not? We would have the data in clear at this stage. But to do all of this was taking like 2 months. All right. So what's the time we needed to do this study that we just showed? So this is the flash bus schematic that we were looking at. And so imagery, less than 2 weeks. And when I say imagery, it's deprocessing the chips, getting every layer, and put the chip inside the SEM and make the pictures. So less than 2 weeks. Then feature extraction, less than 2 weeks. And we did some check, you know, to make sure it was right enough to work with. Then, when we were doing this, I said earlier that we were just in tracing mode. It's not like we get the full flat netlist and try to do something with it. It's we trace, and it's making the netlist as we go, you know. And during that process, we found like 22,000 instances of the standard cell that we extracted. And we found the instruction register in like a day. But to make sure it was the instruction register, so looking at the instruction decoder took just like a week. And it was the longest part of the study. So this whole study is like almost nothing. You know, it's if I remove the imagery and the processing parts, it's like 3 weeks and a half, you know. In 3 weeks and a half, a chip which is supposed to be super secure, which will be in the field for 10 years, will be extracted. So I guess it's important enough that I mention it. But it was a real secure chip. What we saw was a shield, an internal oscillator with a PLL, memory encryption. Every memory was encrypted. The obfuscation of the different parts inside the core. This means that if I was tracing a line, it could almost go to one side of the chip, going back to the other side before reaching a standard cell, you know. So you have a part of the encryption which is here on one side of the chip, when the other part of the same encryption is like a few micrometers away. And when I say micrometers, it's big for the chip, you know. So was the thing. So if we had to follow that with Photoshop, I expect the time to be like 6 months or so, you know, something pretty long. Then linear code extraction, I have to say that this method is still working and that it will still work for some time. There is some countermeasure, I saw some countermeasures, but nothing that you can't bypass. The ROM, you can read it just based on the pictures. And then, yeah, I put hardware custom implementation are questionable. I don't know if at some point in the process, because I'm sure this chip has a crypto processor, and I think the ROM is made for it. But there could be also some custom function, you know, like cryptographic function that are not software coded. It would be hardware coded. But as you can see, you can trace lines, but you can also generate netlists. So it means that if you can find it, and to find it would be like following the ROM a bit more and see where it's branched to something that looks like either a state machine or another controller. And if you can find that, now you can just start to study the custom hardware function. And again, if the chip is on the field for a year or more, you will have a lot of time to study that and to find a hack and produce an exact clone of the card. All right, I will end up with the process. So the fact to automate completely the process of the hardware reverse engineering on this card give us the result to be as fast as I was saying before. Like the real study was less than 2 weeks, you know. And the factor of improvement compared to the Photoshop manual line tracing is like I don't know. It's hard to describe, but it's more than 15. It's huge. And this method is also opening doors. And this is something that for sure I will investigate later. It's, for example, now we have a GDS2. And on my GDS2, I have like a layer which is called active, and it's only the standard cells, you know. And now I can filter the thing I can filter cells on the GDS2, for example, just to see registers or latches. And if I can do that, it means that now if I come with a semi-invasive attack, EMA or laser fault injection, I can just focus on these spots. Because I know that if I put a laser, for example, on top of a combinatorial logic, I don't expect much to happen. But if I do the same thing on top of a latch or a flip-flop, the effect will be more powerful because the value will stay, you know, for the clock cycle, and I will be able to propagate it. So it means I can reduce the attack surface by a factor which is just huge and do the thing like that. But it's not the only doors that are open with this kind of methods, and I don't know, but I hope I will be there next year to show you some more hardware thing. So thank you for your attention. If you have any question, there is a microphone there, but we have like 2 minutes for it. But I will be available right after if you have any question, and we can discuss together if you want. Thank you. Yep, there's a microphone there just for the recording. Or maybe you just say it loud enough that I get it and I will repeat it.
Do you have to full reverse engineer to make a clone? Is the image not enough just to make a clone? Or do you have to understand how the chip works just to... You get my question?
No, not really. I'm sorry.
Do you have to reverse engineer the chip
Yes.
just to make a clone? I mean, for example, the images that you get with the electron microscope,
Yes.
is the images enough to make a clone just copying it?
Almost. I mean, if you, it's almost to understand the architecture. So the question is the pictures enough to make a clone of a chip? So yes and no. It's enough to understand completely the architecture, to find all that must be custom. But you miss one thing, is the memory content. And for the memory content, if there is a flash or EEPROM, you need to extract it. And you can't image the bits inside the flash or EEPROM. So you have to use like a focused ion beam and make an edit to be able to probe and get the things. But that's enough. After it's just enough. Yep.
So a little bit of a question about your deprocessing methods. For delayering, do you have any particular trickery? I know a lot of people are using polishing or chemical delayering or lapping, but those tend to produce somewhat uneven results when you're trying to do a full layer image. Do you have any approaches to that?
Yes. So I didn't hear well enough, but I think it's about deprocessing techniques.
Oh, apologies. I'm just asking if you have any particular technique for evenly delayering.
Oh yeah,
something that's maybe 5 metal layers as opposed to 3.
That's the tricky part. If you want to achieve something very even on the whole surface, you need to combine techniques. I would strongly
reactive
advise
ion etching or anything like that, or
sorry,
reactive ion etching or anything along those lines, or
yeah, no. I mean, you need to have like a plasma machine, chemical mechanical polishing.
Okay.
You need also to have wet chemicals, and if you mix all of that in the right order, you will get a very nice deprocessing, but it's very complicated.
Cool. And maybe just related to that, and sorry if I'm sucking up time, you had mentioned something that I haven't actually seen or done before, where you're removing the bulk silicon and imaging from the backside. What are you using as your chemical recipe, or is that?
Oh yeah, for just making the backside pictures, yeah. That's very easy. That's super easy. You just need to have something that will hold your chip, because when the backside will be removed, you will have like 10 microns of interconnects, metal interconnects inside an oxide with mechanical constraint, which will tend to bend the chip itself.
Well, I know the traditional approach is going from the top side using hydrofluoric or some fluorine.
No, I mean, you can do this, but on modern chips, there's no way this can be used to have like a good result.
Okay, cool. What chemical do you actually use for doing that deprocessing?
I'm sorry, I don't really hear you well enough. You know?
Oh, I was just asking, what chemical are you actually using for the bulk silicon removal?
I use TMAH, like tetramethyl ammonium hydroxide.
Okay, thanks.
Okay, time's up. So if you have any other question, we can discuss later. Thank you.